Every time. Okay, sorry, quick recap. So today what we're going to do is learn how to use or how to conduct a one-way ANOVA in SPSS. The data set that we're going to use is the program.sav data. In learning how to conduct a one-way ANOVA in SPSS, we are going to learn how to restructure SPSS data, check normality for the one-way ANOVA using residual analysis, and check the constant variance assumption using residual analysis or the raw data itself. Okay. When we load the program.sav data into SPSS, which is done in the normal way, so we upload program.sav and then open program.sav, we have the following data set, which is shown here. This data set is composed of 4 simple random samples that are independent of one another. And each sample gives 11 scores. So each sample or each method has 11 students assigned to it. They were all given the same test, and these are their scores out of 10 on that test. And what we want to know is there evidence of a difference between the average score of each method? So this is an ANOVA type experiment because we have more than 2 treatment means, and we're looking for difference across all means at the same time. All right, now the first consideration, which is data restructuring. When we look at the composition of this data, you can see that we have each variable being loaded into its own column. Now, as we know from our previous examples, when we want to compare means, most of these types of tests require that we have a grouping variable and a quantitative variable that are separate from each other. So for example, on lab assignment number 2, in question 1, we have a similar data structure issue. So we have 2 velocity measurements that are given in their own column. And what we need to do is structure the data such that the velocities are in one column, and then we have an indicator beside them to separate them into their 2 groups. This is the same problem here, because if we go compare means, one-way ANOVA, you can see that we have 4 quantitative variables, but there's no factor here. So we need to create the factor. Now there's a few ways that you can do this. There would be what I would describe as kind of a brute force approach. So if you click variable view here, you can insert a new variable in this row here. Okay, it's going to be numeric, and it's going to be a scale value. So I did that by clicking variable view, and then I double clicked here and I just created the scale. And then what I have to do is I would have to copy and paste all of these values over and stack them together like this. Okay. You can see that in some cases, the copy and pasting doesn't work that well. Then I would go back to variable view. I click here. I'll call this factor. This is going to be a string, and this is going to be nominal. All right. And then what I'd have to do is I'd have to insert the factor level for all the variables, which is kind of a pain, and you run the risk of making a fairly big mistake here. Also, the issue is that it didn't copy and paste properly, which is a whole other problem. But this would be how you would approach it. So let's just, for illustrative purposes, do it like this. Okay. I know this isn't exactly correct, but I'm going to show you a better way in a moment. But then what you should be able to do is go analyze, compare means, one-way ANOVA, all values. Oh, cancel. And then here we have to add value label. So you see, like when you do it with this approach, it's very clunky because you're basically kind of making the data yourself. But in the end, you should be able to, well, it doesn't even look like it's going to work in this particular case. Oh, it'll work for the t-test though. So you can use this method for the t-test and that'll work fine, but for the ANOVA, it won't even work at all. Okay. So this is sort of like a clunky, like forced approach that you could use for the t-test example on assignment number 2, lab assignment 2. So you can stack the velocity data together and then create your own column of indicators. And again, that can be done through variable view. You put a name in for the indicator, you change it to a string, you fill the indicator in with the value, and then you tell SPSS which value belongs to which. So this is one approach. The other approach is to use SPSS directly to restructure the data. And this can be done on both lab assignment 2 or any time that we need to build an indicator for our quantitative data. So to do this, we would go data, restructure. Okay, so data, restructure. We're going to click next right away. So the first case is the case that we want. So we click next. Then we click next again. So we want to have this column here, the 1 selected. Then what we do is we take our 4 quantitative variables and we put them into the target variable slot. Okay. Now we can change the name of the new column if we wanted to. So this could be changed to scores_all. So the scores for all students. You don't have to change the name. You can leave it as trans1 if you want. It doesn't matter. It's just a name for the column. Here we click none. So the case group identification is none. Then we click next. We leave this as a 1, so we click next. And then here we leave this as sequential variables, so we click next. And then here we can leave this as it's given. We click finish. Click, yep. And then you can see that what gets outputted here is a data set where we have the index and the scores. Okay, so my recommendation to you at this point is to save the data. So we'll call this program_restructured. And then what we'll do is we'll arrange this. Oh, sorry, one sec. All right. So now we have our rearranged data here. And make sure that this is going to actually work. Yeah. Right. And then what we can do is we can reopen the program data and we can compare to make sure that we didn't integrate any mistakes. So here we have the values 3, 5, 6, 8, 4, 3, 5, 6, 4, 6, 3. So 3, 5, 6, 8, 4, 3, 5, 6, 4, 6, 3. So it looks like it's fine. We'll do a quick check at group 2, 5, 7, 7, 6, 6, 8, 4, 6, 7, 5. Yep. Okay, so now you can see that through the restructuring, we have the data in the form that we have to have it in to conduct the ANOVA. So again, what we're doing here is we're using data restructure, and then we're working through the process of putting the data into one quantitative column and one indicator column. And this is the same thing that we can do on lab assignment 2 in question 1. So we can use the same trick to restructure the velocity data into one quantitative column and then add an indicator beside it. And the process would be exactly the same. You might have to delete some empty rows after you restructure it, but there is a way to actually remove all empty cases as well. You just have to make the right selection on the very last page of the restructuring. Okay, but now that we have the data in this form, we're free to just move through and finish off the rest of the material. So we want to conduct an ANOVA that compares the average for group 1 to the average to group 2 to group 3 to group 4. We have 4 assumptions that we want to check. We have the simple random sample assumption, independent population assumption, normally distributed populations assumption, and we have the constant variance assumption. From the lab manual, the first 2 assumptions we can check off. So these are actually stated in the lab manual. So this was given in the description of the problem. And we have the same thing here. But in general, we know that the SRS assumptions and the constant in the independent population assumption, we can only verify that through problem description anyways. Okay, the next assumption, normally distributed populations. How can we check this? So the way that we can go about checking this assumption is twofold. We can make QQ plots of the individual data points. Okay, so to do that, we would go analyze, descriptives, explore. Then we would put our scores in the defendant factor. We would put our index in the factor list. And then we would click on plots. Okay, so we have stem and leaf and we have so in the box plot column, we have factor levels together. And then we go normality plots with test here. Okay, so again, to check the normality assumption, we have 2 options. The first option, analyze, descriptive, explore. Our scores in the dependent column, our index in the factor column, click plots. We want factor levels together for the box plots. And then we want normal probabilities, normality plots with test. We click continue, we click OK. All right, and then here is the output. So you can see here that what we've created is a QQ plot for each of the different groups, right? So here's our QQ plot for the first group, for the second group, for the third group, and for the fourth group. Now, you'll notice that the plot looks a bit off because there's fewer points on the plot. This is because we have observations stacked at the same value. So students that got the same score on the test. So this approach could work, and we could copy and paste each of these plots into our output and use them to assess normality. But there's another thing that we can do that I'm going to show you in a moment that's more, I think, more appropriate. Now, the last plot that's shown here is a box plot comparing all of the ranges. This plot is useful to us because we can use this to check the constant variance assumption. So I'm going to pull this plot out, and I'm going to insert that here, and we'll come back to this plot in a bit. But this is a good illustration or a good method for checking for constant variance because we can compare the ranges of the box plots to see if there's consistency. All right. Now, the preferred way to check normality. The better way to check normality is to build a residual plot, or is to construct the residuals for the data set and then construct a QQ plot of the residuals. So to do that, we would follow the following process. We would go analyze, general linear model, univariate. Okay, so analyze, general linear model, univariate. We would place our scores in the dependent column and our index in the fixed factor column. Then we click on the Save tab here. Okay, so under the residuals column, we would click Standardized. And under the predicted value column, we would click Unstandardized. Then we would click Continue, and then we would click OK. So again, it's analyze, general linear model, univariate, scores in the dependent column, factors in the fixed column, and then under save, we want unstandardized here, and we want standardized for the residuals. So now if you go back to the data, you can see that this is loaded the PRE_1 value here, and then the ZRE_1 value here. So these are the predicted, unstandardized predicted values. And these are actually just means. So this 4.82 is the mean of group 1. The 6.18 is the mean of group 2. The 7.09 is the mean of group 3, etc. The standardized residual is the difference between the score and its mean. And then it's also standardized. But you have basically 3 minus 4.82 divided by the standard deviation of the group. So these values here are called the residuals. And these are estimates of the normal error term that we attach to the ANOVA model. So basically, we can QQ plot just this data. And if that looks normal, we have evidence of the normality assumption for the whole data set. So this is, I think, the better approach. So what we would do here is then we would go analyze, descriptives, QQ plots. We want the standardized residual values. Okay, and that's it. And then we click OK. And then we have the following plot. And then now we can check the normality assumption. We go back here. And then we can say from the QQ plot shown below, there is no evidence to suggest that the variable of interest is not normally distributed, since the residuals appear to be linear with the quantiles of the normal distribution. Or let's say with the expected normal values. So I admit that up to this point, we've had to do quite a few things in terms of data manipulation and whatnot, but you know, for the normality assumption, this is certainly the preferred approach. And what we're doing essentially is just creating the residuals using SPSS and then plotting or building a QQ plot of the residuals. The first step where we restructured the data, that's only necessary if we don't have the indicator in the data set. So most of the techniques that we look at for comparing means require one quantitative column, one indicator column. So the restructuring is a way that we can add that indicator in automatic, or add that indicator in through SPSS. Okay, so the fourth assumption is our constant variance assumption. So I took the box plots that we created earlier. So these are the box plots for each group. And what we're doing here is we're looking to see if the ranges are similar. And what we can tell here is that this first group has a range of 5, range 4, range 4, range 3. So there is evidence of a difference in a lack of constant variance. Let's use the residuals to check this as well. So to do that, we would go back to SPSS. We would go graphs, legacy dialogues, scatter / dot, simple scatter, and then we would go standardized residual on the y-axis, predicted value on the x-axis. Okay. And then we can call this standardized residuals versus predicted values. Okay. And then we get the following plot. So what this plot is showing us, it's giving us another look at the range of the groups. But in this case, we're considering the residuals rather than the raw data. But we're looking for the same thing here. So we're still checking to see if there's evidence that the ranges are different across the different treatments. Okay, so we can see here. Yeah, which part?
Sorry, the part when you said graphs and then legacy dialogues, I just missed one step, I think.
Okay, yep, legacy dialogues, scatter plot.
Okay.
Define, and then standardized residual on the y and predicted on the x.
Okay, thank you.
All right, so when we examine this, I mean, you can basically see the same issue. We have two groups here. So the group around a mean of 6.13 and the group around a mean of 7.08 or whatever that is, those have about the same range. This value here, or this group here, clearly has a shorter range than the other two, and this group here has a much wider range than all three. So this to me is giving some evidence of a difference among treatment means. Okay, so here we would say the side-by-side box plots and residual versus predicted value plots are giving evidence that suggests the variation in each group are different. But the problem here is that, are they different enough for us to warrant rejection, or for us to say that the variance assumption is violated? The last thing that we can do to help make this decision is actually start the process of the ANOVA. So in SPSS, we're going to go analyze, compare means, one-way ANOVA. Okay. On our dependent list, we'll have the score, and on the factor list, we'll have the index. All right. Okay. Now, inside the options dialog, we have a few different selections that we can choose. And the one that I would suggest here is the homogeneity of variance test. So this here is going to give us a formal hypothesis test about whether or not the variances are equal across the groups. Now you can also select the means plot if you want and the descriptive plot. I mean, you can pick all of these things, but I think that this particular test is probably the most useful. And then let me just check what the Brown-Forsyth test is, because I don't quite remember. Yeah, so the Brown-Forsyth test is the same thing. So we can use both of these to check for a formal hypothesis test about variance equality. So let's choose these two options. Click continue, click OK. Okay, so test of the homogeneity of variances. So we have, based on the mean, a test statistic of 1.269. So that's a p-value of 0.298. So that's actually good, because the null hypothesis here is that the variances are equal, and this p-value of 0.298 would not warrant rejection at the 5% significance level. So visually, we can see a difference in the ranges of the plots, but the formal test of variance equality is not indicating that we should reject the null. However, oh wait. Yeah, equality of group variances based on performing a one-way ANOVA. However, the Brown-Forsyth test, but this says robust test of equality of means, so I don't know if we can actually use this here. This might be something different from, yeah, I think I would be inclined to ignore this. So let's just focus on what's given in this column here. It's a bit misleading, SPSS. Okay, so however, are the ranges different enough to warrant, let's move this part down actually. Okay, so visually, it looks like there's a difference, but the question is, are the ranges different enough to say that the constant variance assumption is not met? Let's use a formal test. So from SPSS, we can insert the following output, and we can see based on each of the criteria, the p-value do not suggest that we should reject the null hypothesis of equal variance across these treatment groups. Therefore, we can proceed with the one-way ANOVA and assume all assumptions are intact. Okay. So just to summarize what we've done here, we've spent the last little while just talking about the assumptions of the one-way ANOVA. The one-way ANOVA itself we'll be able to do very quickly because it's just a standard hypothesis test with 6 steps, and SPSS gives you the output. But checking the assumptions takes more time because we have different ways of doing it. For the normality assumption, again, what I suggest is that you create the residuals and make one QQ plot of the residuals. For the constant variance assumption, we can use comparisons of side-by-side box plots and comparisons of the residual versus the predicted value plot. And we can also use the output from the tests of homogeneity of the variances. So these tests are tests that all variances are equal across the populations. So if we do not reject the null, that means that we're not rejecting, we should not reject. That means that we have no evidence to suggest that the variances are different, which is what we want because the assumption is that the variances are equal. Okay. Does anyone have any questions? Yeah, that's true. Yeah, it would only be the area in the upper tail. Any other questions? All right. Okay, so let's perform the ANOVA test. When we did this variance discussion, we actually ran that through, so compare means, one-way ANOVA. We have the output for the homogeneity of the variances test through the command that gives us the one-way ANOVA output. So right here is the ANOVA table for our procedure. So this is going to be what we use on step 3. And that's just found by going analyze, compare means, one-way ANOVA, the regular sort of setup. So on step 3 here, we can insert our ANOVA table. All right, and all we have left to do is just complete the test. So our null hypothesis is going to be that the variances are equal against the alternative that not all means are equal. We're going to test at the 0.05 significance level. On step 3, we're going to calculate the test statistic. So this is done through one-way ANOVA, or the one-way ANOVA command. So the p-value here is 0.001. So since the p-value is less than alpha, we can reject H0. And then we can say at the 5% significance level, the data provides sufficient evidence to suggest that there is a difference among the mean scores on the standardized test between the 4 teaching strategies. And we're done. All right. Okay, so that's a one-way ANOVA and SPSS. And as you can see, like the hypothesis test itself, it's very straightforward. It would follow just like the other hypothesis tests we've talked about in the last few labs. 6 steps, SPSS does all the hard work for you, and we're really just interpreting the results of the test. The more interesting part of the questions is really the residual analysis and checking for the constant variance and normality assumptions, because that actually requires us to put a little bit of thought into what we're doing and look at different strategies for evaluating the assumptions. Okay, so that's all the material that I need to show you today. So just how to run the one-way ANOVA. Next week, we'll do contrast and multiple comparisons. And then the week after, I think we have lab the week after will be CRBD and maybe two-way ANOVA. And then we'll have reading break. So yeah, I'll hang around if anyone has questions, but otherwise the lecturing material is done. So I'll stop the recording here. But if you guys have any questions, let me know. And otherwise, I will see you next Friday in lab.